For the simply supported beam shown, A, derive the equations for the shear force V and the bending moment M for any location in the beam, and B, determine the max absolute value of the bending moment in the beam. Okay, let's not panic. So we know that dV dx is equal to minus W. Well, in this case, we can say that V is equal to the indefinite integral of minus W dx. Well, we do have the function of W. It's going to be W naught sine of pi over L times x. This is all dx. So what does that mean? Well, that means that we can integrate, and the minus W naught goes away. The minus actually goes away because the integral of sine is negative cosine. We get the cosine of pi Lx. We're also going to need something in front of this, like L over pi. Like L over pi. And then we're going to have plus a C1. Okay. So this is my function, almost done, I just don't know this, for the shear. Now for the moment, we know that the derivative of the moment with respect to x, that's equal to my shear function. So that also means that my moment is equal to the indefinite integral of the shear times x. And we do have a function for the shear. That is W naught L over pi times the cosine of pi over L times x plus C1. All of this, and I'm going to put it in square brackets, all of this integrated with respect to x. And so what do we get here? Well, the integral of the first part is going to be, constants will stay in front, and then this is going to be the sine of pi over Lx, but we must have had a pi over L out there, because it wasn't there. So it must have been L squared and a pi squared. And then we have plus C1x plus C2, right? And this is going to be my M function. So now what do we do? Well, now we need some boundary conditions. We need boundary conditions. Well, I know that M is equal to 0 when x is equal to 0, and M is equal to 0 when x is equal to L. So we can say, substitute those in. So 0 is equal to W naught times L squared divided by pi squared times the sine of 0 plus C1 times 0 plus C2. Okay. Well, sine of 0 is 0. This is 0, so we know C1 equals 0. Now, the second one is 0 is equal to W naught times L squared over pi squared times the sine of pi and plus C2. Sine of pi is 0, so C2 equals 0. So what we get out of this is that my m is equal to W naught L squared over pi squared times the sine of pi over L times x, and my v function is W naught L pi cosine pi over L times x. Now what's cool about this is that this is one of the answers that they wanted, but also we can find when the moment is max by finding when the shear is 0. And so it's really what would make this 0? Well, if pi over L times x were equal to pi over 2. So my x is equal to 1, and we don't have a length, but when that is 1, so my m, I'm going to put 1 into there, is going to be W naught L squared over pi squared times the sine of pi over L. And that should give me my maximum moment. Let's see. That should give me my maximum moment. Oh, hold on. I think I made a mistake. I was reading this as a 2. So if this is L, my bad. Then my x, these will cancel out. My x is going to be at L over 2. And so my m, max, is going to be equal to W naught L squared over pi squared times the sine of pi over L times L over 2. And this becomes a 1. So W naught L squared over pi squared. There you go. So that's my other answer. Okay, so what's the main takeaway from this is just when you don't want to do the shear diagrams, or you're required to use the relationships between the distributed load, the shear, and the bending moment, just integrate and keep the constants and then look at the boundary conditions. All right, I hope this was useful, and I will see you next time.